Let's launch into chapter 3.5, which is about curve sketching. So a bunch of stuff we've been doing in chapter 3.1, 3.3, 3.4 about critical points and inflection points. Those are finding the interesting points of the function, where the function's doing interesting things. And so we can set our x window when we're graphing to include those x values so we see the interesting stuff. Desmos and Excel are great as long as you tell them what set of x values to use. Then you can auto-scale the y-axis, but they have no way of determining what the interesting range of x values is. So here in chapter 3.5, we're kind of putting that knowledge together with knowledge about increasing and concave down and all kinds of stuff. The book has a 7-step process for sketching a graph based only on the formulas for f prime and f double prime, so you should go read that. I'm not going to just read it out loud to you. From f, we can get information on vertical asymptotes and the behavior of the function as x goes to infinity or minus infinity, whether it has horizontal asymptotes. F prime gives us information on where the original function is increasing or decreasing, and if f prime is 0 or d and e, then that's a critical point, and that could be a candidate min or max. I'd want to graph something around there to see what's going on. And if f double prime is 0, then that's a candidate inflection point. Where f double prime is positive, then that's probably concave up, all kinds of good stuff. I would add an 8th step to this whole sketching graph process. If the function is cyclic, like our classic sine or cosine, maybe even tangent, you should ask what's its wavelength, and then your x window should include at least one full wave, probably 2 or maybe even 3, just in case you're wrong about the wavelength being constant. Then you can see, oh, the wavelength was this, and then it got shorter, and then even shorter, or it was this, then it got shorter, then longer again. I think any cyclic function deserves a graph of at least 2 of its wavelengths. How do you determine the wavelength from a formula? Let's take a look at that. So let's say you have something complicated like sine of 2 pi times 440 times x. Our frequency coefficient is whatever is multiplying the x. Here it's 2 pi times 440. And then the wavelength is 2 pi over that frequency coefficient. So here the 2 pi's cancel. You get 1 over 440, or 0.0022727272. Why did I choose 440 here? That's a common pitch in concert hall kind of music, A440. So 440 cycles per second. Actually, it's 440 cycles per second, but this wavelength would be not a frequency like cycles per second, but time per cycle. So that many seconds per cycle. So seconds per cycle. If you want to know where this magical formula of 2 pi over the frequency coefficient comes from, we'll just think of a sine wave, or a sine of 1 times x. Its frequency coefficient is 1, and its wavelength is 2 pi. If you put a 2 in there, things will go twice as fast, and you'll get half the wavelength. So you should have an inverse proportion between the frequency coefficient and the wavelength, and the constant of proportionality should be 2 pi, because that's the fundamental wavelength of sine waves.